record. So it's a great pleasure to have Saul Pace or Pache, I don't know, from MIT, talking about generalized symmetries and ordered phases. Please take it away.
Okay, great. Can you see my screen still?
Yes.
Okay, great. Yeah, thank you for the invitation. I've learned a lot from the Symmetry seminars, and I'm really excited to be able to talk about some of the things I've been doing. And today I'll talk about something that's based on two papers. The first paper is something I put out in August, and the second paper hopefully will be out soon. It's in collaboration with Chenchang Zhu, Agnes Boudry, and Xiaogang Wen. And since this is a Symmetry seminar, I don't have to hype up generalized symmetries too much, but I can't help myself from being a little bit excited about the symmetry renaissance we're in. Over the past 5 years, our understanding of symmetry has undergone a dramatic revolution. And I feel like every month there's new names for symmetries, and it's been a lot of fun keeping up with what everyone else has been doing. And with all these new names for symmetries, I feel like we're looking for a symmetry elephant. You know, the symmetry elephant has kind of always been there, but we never thought that it was all connected, right? We saw the trunk, and the trunk was ordinary symmetries. And then we realized, oh, the tusk is like higher form symmetry, and that's actually a symmetry. And as we explore this symmetry landscape more, we're learning more about the elephant. And we're getting to learn more about both physics and math, which is pretty cool. And the crux of a lot of the generalizations is this point of view that anytime you have a topological defect, it is also a symmetry defect. It's certainly true that anytime you have a symmetry defect, it's a topological defect, but here we flipped it around, right? And this is the perspective I'm going to take in this talk. And the reason that this has been such a fruitful generalization is it passes the duck test. And the duck test says that if it looks like a duck, swims like a duck, and quacks like a duck, that's probably a duck. So by saying a topological defect is a symmetry defect, you always have a symmetry operator that commutes with the Hamiltonian, which is a consequence of the defect being topological in time. There can be objects that carry symmetry charge, and these objects can condense. And when that happens, there'll be spontaneous symmetry breaking, and the topological defect can have Tufts anomalies, so it kind of has all the nice gifts that we're used to in normal symmetries. So let me do a very simple example, which will be relevant for this talk, mostly just to ground us. And we'll consider a superfluid at low energies. So here we're going to be in d equals 3 Euclidean spacetime. I'm mostly going to be working in Euclidean spacetime in this talk. So anytime you see dimension or big D, it's always going to be spacetime dimension. You don't have to do any +1 adding. I know that can be hard. And it's a superfluid phase because it has this symmetry breaking pattern. There's some microscopic U1 symmetry, and that's spontaneously broken down to the trivial group, which I'm just going to denote as 1. And you can characterize the symmetry breaking pattern by looking at this Goldstone boson, this field theta. And it's a map from spacetime to this space M, which is basically a circle, right? So the aspect of this superfluid that I care about the most right now is the presence of one-dimensional vortices, which are defects. And these can be detected by taking some one submanifold of spacetime. This loop is sigma 1. And if this pink line is the vortex, you can detect it by taking sigma 1 and just wrapping it around, okay? And then you can tell you have a vortex that links with sigma 1 by calculating the winding number of theta. And because this M is topologically non-trivial, the winding number will take values in integers, and just simply counts the number of vortices that are linked with sigma 1. Okay. So this vortex, really it's a singularity of the order parameter field theta. Okay. And at low energy, it's not dynamical. It's something you add in by hand to the theory and just sits there. It's never going to break open or anything like that. And at these energy scales, where there's no pair production, the vortex line won't break open, there's a U11 form symmetry. And this U11 form symmetry is generated by the following topological defect. You just exponentiate the winding number, okay? And because the winding number is an integer, alpha will take values from 0 to 2 pi, so that's why we're calling it a U1 symmetry. Furthermore, because the winding number detects the vortex, the vortices are charged under this U1 one-form symmetry. Okay. Now, this is a Euclidean point of view. If we were to go to Lorentzian spacetime, and we looked at the vortex defect in a space, in a time slice, then it would be an operator acting on the Hilbert space, right? And what it'll do is it would create a loop in space, which would then, form a membrane in spacetime, right? And the fact you have this U1 one-form symmetry ensures that this loop number is a conserved quantity. Okay. So the point of this talk is to essentially generalize that example and talk about the emergent generalized symmetries in generic ordered phases. So any sort of symmetry breaking pattern. And as an application, talking about the spontaneous symmetry breaking patterns of these generalized symmetries. So why should you care? Well, that kind of depends on your background. So, I'm a condensed matter person. So the reason I care is that ordered phases are very common. If you look around in your room, probably every single phase that you see in front of you is in an ordered phase. So here we're seeing generalized symmetries emerge in very common places. And furthermore, this application is quite nice because the generalized symmetries can predict exotic disordered phases that neighbor these ordered phases. From a high energy theory point of view, these are going to be symmetries of nonlinear sigma models. And they're going to describe the topological sectors of these nonlinear sigma models. And lastly, from a math physics point of view, firstly, generalized symmetries, by now I think everyone knows, are described by higher category theory. This is certainly true for these generalized symmetries, but even more, they're related to higher representations of a higher group, and that higher group is related to twisted fibrations in a Postnikov tower. There's a lot of very interesting math structure as well. So here's the plan for the talk. First, I want to review some generic features of ordered phases and talk about what I'll call homotopy defects, which are essentially generalizations of the vortices we were just talking about. And after we're done with that review, then we can get into what these generalized symmetries are and talk about the symmetry category that describes them when they're finite symmetries. And then lastly, as an application, we'll talk about what happens when we spontaneously break these symmetries. And we'll give examples throughout the entire process. But in this third section, we'll actually look at some lattice models and some field theories as well. So let's begin. So an ordered phase, just as a definition, is a phase where there's an ordinary internal symmetry G and it's spontaneously broken. Nothing fancy. It doesn't have to be an internal symmetry. For example, if you have a space-time symmetry spontaneously break, you can get things like crystals. But for the purpose of this talk, I really only want to restrict to internal symmetries. It's just simpler. And all the universal features of an ordered phase is determined by what's called the symmetry breaking pattern, which roughly speaking, you just need to know the subgroup H of G, which the symmetry is spontaneously broken down to. And given G and H, you can put labels on what the different ground states are. And the space that these labels form is something I'm going to call the order parameter manifold. And it has a bunch of other names, but this is the name I'm going to use in this talk. And just this left coset, G mod H. And the point of G mod H is because the ground states don't transform under H, it just puts a label by modding out H. And then lastly, which is probably the most important part of the story, is that when you have an ordered phase, there can be gapped objects or massive objects, which I'll call homotopy defects. And these are characterized by the topology of the order parameter manifold M. So just to give some names, things like domain walls are technically homotopy defects. We just saw vortices, and they're technically homotopy defects. Hedgehogs, not the animal, but the defect is a homotopy defect. Sometimes these are called monopoles. There's many names for them. And as a warning for any condensed matter people, I think homotopy defects used to be called topological defects. Not because they're topological in the sense we mean now, but because they're characterized by the topology of M. But anytime I say topological defect, I really mean it in the sense of a symmetry defect. And anytime I say homotopy defect, I mean these types of defects. Okay. So, there's a question?
Yeah. Are these dynamical excitations or are these defects?
Good. Yeah, that's what I'm going to talk about right now. I'm gonna abuse terminology and call them defects, even if I really mean they're dynamical. Um, but yeah, the point Nati is making is from an IR perspective, they're really defects and they're not dynamical. Uh, so yeah, if we're living in low energies and we have a continuous group G, we'll describe the ordered phase by some effective field theory using some coset construction, and the effective field theory will just be a nonlinear sigma model. And the target space will be the order parameter manifold G mod H. And the point of this effective field theory is to describe the low energy fluctuations of any Goldstone bosons. Okay. And in this context, the homotopy defects are singularities of the order parameter field. There's something you have to add in by hand. They're not dynamical. You can think of them as they're like infinitely massive versions of the genuinely dynamical versions. If G is finite, the effective field theory is actually a TQFT. And it just describes the symmetry broken ground states or the superselection sectors. In this case, there's also homotopy defects. And now they're just certain G symmetry defects. But they're also not dynamical. The Hamiltonian is always 0 of a TQFT. So from an IR perspective, homotopy defects are not dynamical. There's something you add in by hand and they just sit there. Okay. But from a UV perspective, this is not the case. A generic UV theory, and when I say UV theory, I really just, I'll always mean lattice model. The homotopy defects are generally dynamical. So maybe I shouldn't call them defects, but it's kind of the standard terminology in condensed matter to still call them defects, even though when they're dynamical. So I'm just going to follow that tradition. And the fact that they're dynamical, we actually use that in condensed matter to label the phase diagram. It's pretty common. So here's kind of the prototypical phase diagram with an ordered phase. So you have the ordered phase, and there's a symmetry broken pattern. G gets broken down to H, and there's these gapped homotopy defects we're talking about. And this is the phase diagram of some UV, some lattice theory. So if I go really, really deep into the IR, there'll be some continuum low energy description. And if G is continuous, it'll be this nonlinear sigma model people are probably very familiar with. On the other hand, I can undergo a phase transition. I have some tuning parameter G. I have G be larger than some GC, and I'll go to a trivial disordered phase. Disordered really just means that this symmetry G is not spontaneously broken. And I'm just calling it trivial because it's the continuum description deep into this disordered phase is just a trivial field theory. Now, the fact that these homotopy defects are dynamical means that we can proliferate the defects. And the common perspective of this transition is that it's driven by proliferating the homotopy defects. And from an IR perspective, when I say proliferate the defects, one way you can think of it as it's like I'm summing over all insertions of the defect and essentially trivializing them. There's no notion of these gapped objects in the spectrum anymore. What that means is that when G is finite and these homotopy defects are symmetry defects, like I mentioned in the last slide, this proliferation could be modeled from an IR perspective by orbifolding. Okay. But more generally, you shouldn't always think of it as orbifolding. So Nati, does that answer your question at all?
Not quite, but please go on. I'll ask you again later.
Okay, sounds good. Okay, good. So an important part of the story will be understanding how these homotopy defects are classified. And because they're characterized by the topology of M, they'll be classified by some topological properties of M as well. So suppose we have some homotopy defect, and it's detected by some case submanifold sigma k. All the homotopy defects that could be detected by this case submanifold are classified by looking at the maps from sigma k to the order parameter manifold. You can think of these maps as coming from looking at your ordered parameter, your order parameter field, restricting to the values it takes on this submanifold and looking at the maps restricted to that. But you don't look at all the maps. You look at these maps modulo homotopy. Okay. And by homotopy, I really mean unbased homotopy. So a very simple case, which is the case I'll primarily talk about, is when this sigma k can be deformed into a k-sphere, the defects are detected just by linking. So that also means they're codimension k plus 1. So codimension with respect to space-time. And now we're looking at maps from k-spheres to some space, so the classification becomes based on the homotopy groups. So in particular, it's not just the homotopy groups by themselves, it's the homotopy groups modulo some action of pi1 on pi k. So this action, you can represent it as this group homomorphism from pi1 to the automorphism group of pi k. Furthermore, I only care about in d-dimensional spacetime k up to d minus 1. The higher homotopy groups are things that they'll tell me about homotopy defects that I can't see in the dimension I'm in, because the homotopy defects pi k tells me about are codimension k plus 1, right? So when k is d, then I'm talking about, minus 1 dimension homotopy defects. These are something I can't see in that dimension, right? And then just to give you, these things are essentially generalizations, these alpha k's, they're generalizations of the inner automorphism. The inner automorphism is pretty simple, it's just conjugation. So that means that when k is 1, codimension 2 homotopy defects, they're classified by the conjugacy classes of pi 1. Okay. So of course, when pi 1 is abelian, it's just pi 1, because the conjugate class will be the same as the group. But when pi 1 is non-abelian, which pi 1 can be non-abelian, but all the other higher homotopy groups are always abelian. When pi 1 is not abelian, the conjugacy classes are very important to include. So let me give an example. And we'll go back to the nice picture that was on the title slide, which is it's called a pneumatic liquid crystal. If you know LSDs or LCDs, liquid crystal displays. It's that type of liquid crystal. So this is an ordered phase where there's a symmetry breaking pattern. SO3 gets broken down to O2. In the order parameter manifold, you can show SO3 mod O2. This is the same as RP2, which is the real projective plane. So let's restrict ourselves to d equals 3 spacetime. So we only care about pi 0, pi 1, and pi 2. And you can show pi 0 is trivial, pi 2 is z2, sorry, pi 1 is z2, and pi 2 is z. And so since pi 1 is abelian, we don't care about what alpha 1 is. It doesn't do anything. But because because pi 1 is non-trivial and pi 2 is non-trivial, we should care about alpha 2. And you can show that alpha 2 will flip the sign of pi 2. So what that means is that the codimension 3 homotopy defects, the sign isn't important for their classification. You can go from a +1 codimension 3 homotopy defect to a -1 codimension 3 homotopy defect just by deforming things. So because pi 1 is z2, you have z2 strings. And because pi 2 is z, modulo the sign of z, you have particles that are labeled by non-negative numbers. Good. So that was the lightning review of ordered phases and homotopy defects. And now I want to get into how there's actually a topological defect hidden in this story. And it's really apparent if you're thinking about how the homotopy defects are classified. Since they're classified by these set of maps modulo homotopy, it means that whatever defects there are detecting the homotopy defects, they have topological properties. So for instance, this is essentially the picture I drew with this superfluid example. If we have this homotopy defect, which is this pink line, and it's detected by this defect shown in green, we can deform sigma k. And as long as we don't have sigma k go through the pink defect, it'll still detect it, right? Of course, if the pink defect ends, we could wrap it around. But if you suppose it doesn't end, then it has to go through the pink defect, right? Therefore, these maps from sigma k to m modulo homotopy depend only on the linking number between sigma and c when c doesn't have a boundary, okay? So when the homotopy defects can't be cut open, or equivalently they can't end, which is to say that there's no boundary, they're detected by topological defects. And if we put that in symmetry words, what this means is that they carry a symmetry charge of some generalized symmetry, which I'll call S pi. Okay. And there's a simple class of examples like this known. So if you have very simple homotopy defects, I'm calling them abelian homotopy defects because all their homotopy groups are abelian. There's nothing subtle going on with the topology. And furthermore, all the homotopy groups will just be Z's, okay? When this is the case, the number of homotopy defects detected by some K submanifold is just given by integrating some K form. Now this K form has some general definition. Is the generator of the Kth Durham cohomology of the order parameter manifold M pulled back to spacetime. So the superfluid example is arguably the simplest example of this type of of K form is equal to 1. And we pull back from the first theorem cohomology using the order parameter field. And then this omega 1 is d of the order parameter, right? And then generally, when there's no homotopy defects, d of sigma will be 0. But when there are homotopy defects, which is the fact that this detects the homotopy defects, d of omega will be c hat, where c hat's the Poincare dual of the homotopy defects location. Okay. So what that means is we have a topological defect, and you can build this by exponentiating this Q, just like we did for the superfluid case. And its job in life is to tell us where the homotopy defects are. And because Q is always Z, this alpha will always, again, go from 0 to 2 pi. So it's all of these are U1 D minus K minus 1 form symmetries. So before getting into more general symmetry breaking patterns and talking about the symmetries more generally, I want to make a point that I think is really important, which I already alluded to. And it's how in generic UV models, these homotopy defects are dynamical, right? And what that typically means is there's some high energy process that cuts them open. You can really think of this as being the same as if I give you U1 gauge theory and you consider pure U1 gauge theory, you have the electric one form symmetry. But if you consider U1 gauge theory with electric matter, the electric one form symmetry is explicitly broken, right? Because the Wilson loops, while always closed at low energies, now they can be open or now they can end on the right. And just like how the electric one form symmetry in that example is not a microscopic symmetry, in generic UV models with ordered phases, S pi is not going to be a symmetry in the UV. However, in the IR, when these homotopy defects are no longer dynamical, so it's like in U1 gauge theory, below the energy scale of the electric charge mass gap, you'll have an emergent symmetry, and it's no different from here. So in the IR, you'll have this S pi be an emergent symmetry. So the mantra I want to drill into your head is that generic ordered phases have generally emergent generalized symmetries. And there's a fun game you can play where you go to some intermediate energy scale where some of the homotopy defects are dynamical, some of them are not dynamical, and what the emergent symmetry is will depend on that precise energy scale you're at. This for simplicity, I'm always going to be implicitly referring to S at the lowest possible energy scale where none of the homotopy defects are dynamical. Okay. And the reason I think this is important is I think it reflects something that's quite general about generalized symmetries in practice. You take your favorite UV theory, and it usually has no symmetries or only ordinary symmetries. In high energy, your UV theory is quantum gravity, and there's no symmetries, or that's the belief, right? And in condensed matter, our UV theory is some Hamiltonian describing some material, and it'll include a bunch of very simple two-body terms, and those simple two-body terms will typically break any sort of generalized symmetries that we may care about. However, in some mid-IR scale or some IR scale, there could be emergent generalized symmetries. Now, usually emergent symmetries get a bad rap, but emergent higher form symmetries are really powerful because of some robustness properties of higher form symmetries. And in fact, I would say, once when you have an emergent higher form symmetry at any lower energy scale, it's as if you have an exact symmetry. You shouldn't think of it as an approximate symmetry. And there's many papers on this from different perspectives, but I think the simplest one is if you have some emergent symmetry, it's an approximate symmetry because you can add a term to your low energy action that explicitly breaks it. However, higher form symmetries, the terms you would have to add that explicitly break it are non-local. They'll wind around space-time, right? So no low energy local action will ever allow you to add such symmetry breaking terms. I think another point that is really important on this point is one of the exciting parts of generalized symmetries, at least for me in condensed matter, is this prospect of a generalized Landau paradigm. And I think it's really, really important that we say, well, generalized Landau paradigms is a classification scheme about emergent generalized symmetries. Our UV theories, the models whose phase diagram we want to explore, won't have these generalized symmetries. However, because they're emergent symmetries, and when they're higher form symmetries, they're exact emergent symmetries, we can still use generalized symmetries to label the phase diagram. Okay. So let's talk about the symmetry more generally. And now I want to ask, well, what is this generalized symmetry? We know there's topological defects, they're detecting the homotopy defects, but I want to have a label to label the generalized symmetries by, and I want this label to tell me how the symmetry defects fuse. So before building up to the answer, let me just tell you the answer right now. It turns out that this generalized symmetry is actually the magnetic symmetry of some higher gauge theory. And the higher group will be a D-1 group whose data I'll tell you all about in like 4 or 5 slides. When there's a finite number of homotopy defects types, this higher group, this D-1 group, is a finite higher group. And in that case, the symmetry S will be a finite symmetry. And when you have a finite symmetry, then the symmetry defects will be described by some fusion higher category. And in this case, it's a D-1 category describing the D-1 representations of this D-1 group. Okay. So this is like crazy complicated. Let me give some very simple examples before going back to this general land. And we'll just consider G equals SO3. And after these papers, I think G equals SO3 is my favorite group right now. But anyways, so the first example, let's be in D equals 3 spacetime. And we'll have SO3 break down to nothing, okay? And in that case, in D equals 3, there's an emergent Z2-1 form symmetry. And if we were to condensation complete the fusion category, we could say that the fusion 2 category is 2 rep Z2. It includes a Z2-1 form symmetry and includes 0 form symmetries, which are condensation defects. Another example, which is more interesting, is now we break SO3 down to Z2 times Z2. And in this case, there's no invertible 1 form symmetry anymore. You actually have a non-invertible 1 form symmetry. And the fusion category is now 2 rep Q8. Q8 is a quaternion group, actually. And then another example is if you break SO3 down to SO2, this is like your ordinary like fridge magnet as the symmetry breaking pattern. And I actually don't even know what label to put to describe the symmetry defects because this higher group is not finite anymore. It'll be a 3 group because we're in D equals 4. And the higher group, you can think of it as like some sort of extension of a 1 form symmetry, a Z1 form symmetry by a Z2 form symmetry. And it'll have a non-trivial 4 cocycle describing the extension. So this example we'll talk about way more detail later on in the talk, and we'll also talk about the symmetry breaking patterns of these emergent symmetries as well. But before that, let's talk. Let me try to convince you why this is the right description for these symmetries. And we'll go in baby steps.
Can you elaborate on the last line? The last line in the table?
Yeah, for sure. So I'll elaborate this in more detail, but let me just give you a quick punchline. The target space is S2, and S2 has a non-trivial pi2 and a non-trivial pi3. So naively, you may think, oh, well, I have in D equals 4, I have 0-dimensional Z homotopy defects and 1-dimensional Z homotopy defects. However, the homotopy defects actually interact non-trivially, which is reflected mathematically in the fact that this is a non-trivial extension. So what you should think of it as is that the 1-dimensional, the strings, those homotopy defects carry the charge of the 0-dimensional homotopy defects as well. That's kind of how the mixing is manifested. So a very vague way I could say this is pi2 and pi3 aren't independent from one another. In a way I'll make precise in a few slides.
In this case, S pi is then supposed to be the 3 rep of that 3 group, or?
I'm a little uncomfortable to say that.
Yeah.
Okay, I think that's true. Okay, good. Yeah, it should be the 3 rep of this 3 group. I'm uncomfortable to put a label like this because this is not finite.
Yes. So what is S pi? Like, do you have a description of S pi in that case?
No, I don't have I don't know how to mathematically describe it. Besides just knowing that there's non-invertible symmetries. We'll see this example in a little bit.
So just to make sure I understand, are you saying that in this case, there's a conserved 0 form charge? associated with pi 3 of
There
x2?
is, but its conservation also depends on pi 2. You know, like the pi 3, you can think of it this way, like the pi 3 tells me that there's a zero-dimensional particle. And I can detect that if I take the 3 submanifold of pi, pi 3 will be when the 3 submanifold is a 3 sphere, right? But I could also have the 3 submanifold be something that's topologically not a 3 sphere. And it can be something that actually, you know, engulfs the strings, right? And it'll turn out that those topological, those homotopy classes also detect the strings. So yeah, let me move on, and I hope it'll become clear what's going on.
Do you have a conserved current for this zero form symmetry or not?
No, I don't know how to think of the symmetry group, or I don't know how to think of the actual symmetry. You should think of G3 as like more describing the symmetry charges, not describing the symmetry defects. I don't know how to generally think of the symmetry defects, actually.
Okay, Shuang is again on the train, so I'm going to read out his comment. You really need to get the microphone, Shuang, to start to speak on the train. I thought there is a non-invertible zero form symmetry in the last line, he's saying. Yeah, I think that's what you're sort of saying too, no?
Yeah, there is a non-invertible zero form symmetry. Yeah, so just to make it extra clear, this 3 group is not describing the symmetry defects. If it were, then there would, of course, be no invertible symmetries. It's really like the 3 representations of the 3 group that describe the symmetry defects. But that's some beast of a mathematical object that I don't have a physical interpretation of. Yeah. Okay, so yeah, let me try to convince you why these higher representations of higher groups are relevant, but I really want to go in baby steps. So like this is the simplest case that people may even be familiar with already. And we're going to consider what I'm calling abelian homotopy defects. So in this case, all the homotopy defects of different dimension are totally independent from one another. And furthermore, all the pi 1 actions are totally trivial, okay? So all the defects are, the only information you need to know to classify the homotopy defects are the homotopy groups. It's the simplest case. And this is the type of case that's talked about in standard textbooks. Because the homotopy defects are classified directly by pi k, the symmetry charges of the emergent symmetry are also described by pi k. So pi k describes the symmetry charges, and the homotopy defects are codimension k plus 1, so it'll be a d minus k minus 1 form symmetry. And these are always going to be abelian, this by the restriction we're looking at. So the symmetry group describing this d minus k minus 1 form symmetry is given by the Pontryagin dual of the kth homotopy group. So if pi k is Zn, this will be like a Zn symmetry. If pi k is Z, this will be like a U1 symmetry, which actually covers that example with the topological currents we saw a little while ago. So now let's graduate. So a slightly more complicated example. We'll consider codimension 2 homotopy defects and ignore any of the other codimension homotopy defects. We'll just assume that they don't interact with pi 1 in any interesting way. But what's different about the last example is we'll consider general pi 1. So pi 1 could be non-abelian here. Of course, when pi 1 is abelian, it'll reduce to the last slide. Since we only care about pi 1, we don't need to know all the information of the order parameter manifold M. So let's truncate M to this truncated space M1, where M1 is defined such that the first homotopy group is the same as the first homotopy group of M, but all the other homotopy groups are trivial. So there's a nice way to say what M1 is. It's just the classifying space or the delooping of pi 1. Okay. So all the symmetries that arise from the codimension 2 homotopy defects of M, they'll be the same exact as the symmetries that arise from M1, this truncated space. Because M1 is the classifying space of pi 1, the homotopy defects will just be the same as the magnetic defects of pi 1. And you can check this for yourself. It's simple. Anytime you have discrete gauge theory, you know that the magnetic defects are classified, the codimension 2 magnetic defects are classified by the conjugacy classes of the gauge group. That's exactly how the codimension 2 homotopy defects of M were classified, right? They're classified by the conjugacy classes of pi 1. Since the homotopy groups are the magnetic defects, what that means is that the symmetry S is just the magnetic symmetry of pi 1 gauge theory. Okay. So when when pi1 is finite, we can write down what the fusion higher categories that describes it. It'll just be formed by the d-1 representations of pi1, which this will always include some d-2 form symmetry. When pi1 is abelian, this d-2 form symmetry is invertible. But when pi1 is non-abelian, this d-2 form symmetry is non-invertible. And the topological defect lines generating the d-2 form symmetry will fuse according to the representations of pi1. Okay. And actually, you could have snelled the fact that there's a non-invertible d-2 form symmetry. You could have snelled this a long time ago. You know, the moment you know that these homotopy defects are classified by the conjugacy classes, well, when pi1's abelian, the conjugacy classes are the same as the group, so it spells like a normal invertible symmetry, right? But when pi1's not abelian, then you're talking about symmetry defects, symmetry charges that fuse according to the conjugacy classes, and that doesn't smell like an invertible symmetry. So, yeah, so you can have told there's going to be non-invertible symmetries in this simple case a long time ago. Okay, so now we're ready to consider the general case, and I'm going to restrict myself to connected M. More precisely, I'm going to assume M is a CDW complex, but that's details that aren't that important. So we're considering general connected M, and we're in D dimensions. But remember what I said, you know, the homotopy groups, the really, really high homotopy groups don't tell me about anything regarding the homotopy defects in the dimension I'm in, right? When K is greater than D-1, it's giving me information about things I can't even see in the space-time I'm in, right? So we don't need that information. Let's not make our lives harder by including it. So let's truncate M to this M sub D-1. And you can introduce something that's more general, M sub N. I'm not saying that tau less than or equal to N. I'm just saying N. Where M sub N is defined such that all the homotopy groups for K less than or equal to N are the same as the homotopy groups of M. But all the other homotopy groups are 0, okay? And you know, just like before, because this truncation knows everything about the homotopy groups that we can actually see, the symmetry from M is going to be the same as the symmetry from this truncated space. Now, this is a well-known thing in math, these truncations, and this M sub N is called the nth Postnikov stage of M. There's a so-called Postnikov tower of M. And it's a model, M sub N is a model for connected homotopy N types. And this Postnikov tower is well known in the math literature. Each Postnikov stage obeys the following fibration, where the fiber is this Eilenberg-MacLane space, or like this nth classifying space of pi n. And these fibrations are classified by twisted n+1 cocycles. And these are called Postnikov n+1 invariants, or Postnikov classes. And it's twisted, and this is the symbol I'm using to really show it's twisted. And it's twisted by the pi1 action on pi n, so this group homomorphism. The twisting just means that the codifferential of this cohomology, the first term in that codifferential will be twisted by this pi1 action. Okay. So this is general. If you've never seen this before, don't worry about it. The point is all this data is the same data as an n group. In particular, this truncated space, the nth Postnikov stage, is the same as the classifying space of some n group, which I'll denote as G sub pi. And the data defining the n group is exactly what's shown above. It's all the homotopy groups, pi1, pi2, all the way to pi n. It's all the pi1 actions, you know, ignoring alpha 1, but alpha 2, alpha 3, all the way to alpha n. And it's all these twisted Postnikov invariants. So in this example I showed a few slides ago, I said something about, oh, pi 3 and pi 2 aren't really independent from one another. And that's some vague way to say that the fourth Postnikov invariant is actually non-trivial in that case. And I'll say more about that later on in the talk. But yeah, going back to this, because you know the symmetry is the same as the nth Postnikov, as if we were considering the nth Postnikov stage of the d-1th Postnikov stage of M. Well, this is this BG for some n group, right? So the homotopy defects are really the magnetic defects of this d-1 group. Okay, and this is a straightforward generalization of what we saw before. Before we only cared about pi1, so we got rid of all this extra datas, and we only had pi1, and then the d minus 1 group is a super trivial and it's only pi1, right? And because the homotopy defects are the magnetic defects, and because the symmetry defects role in life is to detect the magnetic defects, or the homotopy defects, well, the symmetry will be the magnetic symmetry of this d minus 1 higher gauge theory. Okay, and this is an absolute beast. I don't have any physical understanding for the super general case, but there's a nice symbol you can put for finite d minus 1 groups. It'll just be described by the d minus 1 representations of the d minus 1 group. Okay. Okay, good. So this is the general mathematical description for it. So let's just do a quick check-in to see what we've talked about so far. You know, in the d pi r, the homotopy defects of ordered phases carry the symmetry charge of some emergent generalized symmetry S. And what we just showed is that this symmetry S is the same as a magnetic symmetry of some d minus 1 higher gauge theory. And this S is a beast. It includes invertible and non-invertible, zero form and higher form symmetries. There's a bunch of condensation defects involved. And this is all very nice, but now let's ask, well, what are the physical applications of S? And there's two that I know of. I only have time to talk about one, unfortunately. The one I'm going to talk about is, well, we have a symmetry and we could spontaneously break it. So what happens? So that's what we're going to talk about. There's another very nice story that I just don't have time to talk about, is that, well, we have a new symmetry. Maybe it came with some anomalies. And I think S by is anomaly free, but there's a very nice story about there being a mixed anomaly between the emergent symmetry S and the microscopic symmetry G. But yeah, we don't have the time to talk about that, unfortunately. So, but before we get into the symmetry breaking part of the story, let me just pause, see if there's any questions about what we've talked about so far. Okay. Okay, good. So let's start with some general remarks. Firstly, maybe you're saying, well, why are you saying we can spontaneously break S? Maybe it was already spontaneously broken in the ordered phase. Well, that's not the case. S is not spontaneously broken in the ordered phase. Here's a cheeky way to know why. Well, if it were, ordered phases would have ground state degeneracies depending on the space's topology and have exotic gapless modes like photons. That's clearly not the case. So clearly S is not spontaneously broken. Maybe a better perspective is a hallmark feature of the homotopy defects in these ordered phases is not only are they gapped extended objects in the spectrum, but they're also confined in the IR. And what I mean by confined, I just really mean they satisfy some area law in whatever type of like nonlinear sigma model type theory you try to calculate it. And that's key diagnosing criteria is to say the symmetry is not spontaneously broken, right? But just because it's not spontaneously broken in the order phase, nothing's preventing us from spontaneously breaking it, right? And doing so will drive a transition out of the ordered phase. And we just saw, these symmetries are very exotic. So you can expect these neighboring phases will be quite exotic as well. And furthermore, physically, what it kind of means to spontaneously break it, well, the homotopy defects will satisfy perimeter law. That's like what you calculate. But physically means now the homotopy defects will deconfine. Okay. So, well, what happens to the microscopic symmetry G, which was spontaneously broken in the ordered phase, when we spontaneously break the symmetry S? Well, here's a physical argument. So in the ordered phase, as I just mentioned, the ordered vacua want to confine the homotopy defects. However, the generalized symmetry S, when that spontaneously breaks, its vacua it has an S symmetry charge condensate, and that wants to deconfine the homotopy defects. This wants area law, this wants perimeter law. The latter is going to contradict the former, right? So if we're going to be able to spontaneously break S, we better restore the symmetry G. And this actually gives rise to two prototypical types of disordered phases. There's a disordered phase we already talked about. Recall there's the ordered phase that has a symmetry breaking pattern. We just now talked about how there's an emergent symmetry that's not spontaneously broken, and there's gapped homotopy defects. And if we proliferate the homotopy defects, we go to a trivial disordered phase. This microscopic symmetry isn't spontaneously broken anymore. Because we proliferated the homotopy defects, this symmetry doesn't emerge anymore. It's the normal story. However, suppose we were to not allow the homotopy defects to proliferate. So in other words, we add some sort of homotopy defect suppression, which is a strategy used in the past by people in condensed matter to get some exotic phases. Well, now the order phase will be the same with gapped homotopy defects. However, the homotopy defects aren't allowed to proliferate, so maybe we can never have a disordered phase. We just talked about a mechanism to get a disordered phase, right? Instead of proliferating the homotopy defects, we can just spontaneously break the emergent generalized symmetry we've been talking about. So we spontaneously break the emergent generalized symmetry. C is like some subcategory, just some label to say that there could be some residual symmetry left over. However, this is definitely not a trivial disordered phase, right? Firstly, the homotopy defects, they're not proliferated, they're gapped and deconfined. We've spontaneously broke some generalized symmetry. So in the deep IR, this won't be a trivial theory. It could be like Maxwell theory or some TQFT or something like this. While there's been examples of this in the literature before, I really think the perspective to take is, these generalized symmetries offers a unifying framework to think of these non-trivial disordered phases. In addition to giving a framework to think about them, I think it also emphasizes one of the powerful aspects of symmetry, where it's a non-perturbative tool that we can use to identify these exotic phases, neighboring ordered phases. You can be given information of the ordered phase, you can identify the symmetry, and then you can make statements about what possible non-trivial neighboring disordered phases there could be. So let me give some examples. The first is the superfluid example we saw early on. We just had a U1 symmetry and it spontaneously broke, right? Okay, there's emergent symmetries in that story, but those can't spontaneously break. And because those emergent symmetries can't spontaneously break, we kind of have a type of a no-go result. Well, there's no non-trivial disordered phases then. Well, here's another nice example, which I think is quite cool. Instead of considering a normal superfluid, you can consider a so-called two-component superfluid. Like you have two species of bosons that condense. In terms of the symmetry breaking pattern, what that means is you have a U1 times U1 symmetry, and that spontaneously breaks. It turns out you still have, in D equals 4, you still have two of the U1 two-form symmetries that you would naively expect. But now there's an additional U1 one-form symmetry. And that U1 one-form symmetry can spontaneously break. So we have information, you have some two-component superfluid, and we automatically know that there's some interesting neighboring phase that's described by Maxwell theory in the deep IR. Another interesting example is this SO3 example that I think I gave in a few slides earlier. You have an SO3 symmetry, we could spontaneously break it down to nothing. There's a Z2 one-form symmetry, and that Z2 one-form symmetry can spontaneously break. So we have this weird type of magnet, and now we can see that, well, there's an ordered phase, there's a disordered phase neighboring my magnetic phase that has Z2 topological order. That's described by BF theory in the ground states. And then the last example, which is that I'll give on this slide, is the one with the quaternion group. So we had SO3 spontaneously break down to Z2 times Z2. I said there was this 2-rep Q8 symmetry in D equals 3. Well, that 2-rep Q8 symmetry, it has this non-invertible one-form symmetry. I'm labeling it by rep Q8-1. Just say the topological defect lines fuse according to rep Q8. And that symmetry can spontaneously break down to nothing, and we'll actually go to a phase described by the deconfined phase of Q8 gauge theory. Okay. To connect this to some of the more general things,
How? Can I ask?
Yeah, what's up?
Do you know how that symmetry then acts on these different phases? Like it's a spontaneous broken phase, and now you have this rep Q8. Does it still act on these different configurations of Acura?
So I'll actually show this example in a bit, but you should think of the symmetry acting as the Wilson lines or the Wilson loops of the Q8 gauge theory. I don't know how to relate it more to the ordered phase. One thing I can say is the fact that you have maybe you're asking is there anything signaling that we started our life in this ordered phase? And there actually is. The SO3 symmetry still exists in this Q8 deconfined phase.
Okay.
And it turns out that you can show this is part of the Tuft anomaly story I don't have time to talk about, but the SO3 symmetry fractionalizes. And the gauge charges of this deconfined phase carry fractional SO3 symmetry charge. But yeah, we'll see this example in a bit.
Awesome.
Okay,
Sorry,
good.
what session?
Yeah, what's up?
Wouldn't it be the Z2 times Z2 symmetry that fractionalizes? Like the remaining zero form?
No, it turns out that's not what happens. I think I'll show this example in like 2 or 3 slides, and I'll specifically comment about why it's the SO3 symmetry for you.
Thanks.
Okay. Are there any other questions? Okay. To connect this to the general results from the last slide, anytime you have the D-1 group be finite, which is to say there's a finite number of homotopy defects, there's always one of these non-trivial disordered phases. And it'll always be described by the deconfined phase of untwisted this D-1 higher gauge theory. Okay. So for the rest of the talk, I just have 2 examples I want to give that I think kind of, summarizes everything we talk about. We'll talk about the emergent symmetries. We'll talk about their spontaneity breaking patterns. Both of them, we start with G equals SO3. So this is the first example. So it's fun with SO3 part 1. And what we'll do is we'll consider the symmetry breaking pattern where SO3 gets spontaneously broken down to any finite subgroup H. And we'll restrict ourselves to be in D equals 3 dimensional spacetime. So the order parameter manifold is this SO3 mod H. And you can show that, because we're in D equals 3, we only care about the homotopy groups up to pi 2, right? And you show that pi 0 and pi 2 are trivial, whereas pi 1 is non-trivial. And it's actually, H tilde. H tilde is not always the same as H. H tilde is the cover of H that lifts it to a subgroup of SU2. So for example, if H is a Zn, then H is the same as H tilde. H tilde is also Zn. Whereas if H is Z2 times Z2, H tilde is not Z2 times Z2, H tilde is the quaternion group Q8. So, in some of the examples, I showed that the symmetry breaking pattern of the quaternion group came up. You maybe thought like, who ordered this? Why is the quaternions coming up in my life right now? And this is why. So we have the only homotopy defects we have are classified by pi 1. And remember, generally, they're codimension 2, so in D equals 3, there'll be one-dimensional homotopy defects in spacetime. And it'll be classified by the quantity classes of this H tilde, right? And then we could use some of the general results that we just discussed, and we automatically can write down what the emergent symmetry is. It's just described by this fusion 2 category, 2 rep of H tilde. So now let's talk about the symmetry breaking patterns of this emergent symmetry. And we'll do so by building a Euclidean lattice model that can realize this symmetry broken phase. Now there's a naive guess you may have of how you should build the model. You may think, oh, I know nonlinear sigma models. So maybe what I should do is I should have degrees of freedom on the sites that take values in the order parameter manifold. That smells like nonlinear sigma models, right? Where you have fields and a map to the target space, which is the order parameter manifold. But there's an issue with that, though. You don't really have good control over the homotopy defects. So instead, we'll consider a different presentation of the order parameter manifold. For people familiar with the Villan representation of superfluids, it's kind of a generalization of that story. So instead of considering degrees of freedom on lattice sites that take values in the order parameter manifold, I'm going to consider degrees of freedom on the lattice sites that take value in SU2, which I'm calling this G tilde because it's the double covering space of G, which was SO3. So we have, we have SU2 rotors. Don't worry about the name rotors if you've never seen that. It's just to say that there's degrees of freedom on sites, and they're described by some 2-dimensional complex vector Z under the constraint that Z dagger Z is equal to 1. Okay. You can, it's easy. This parameterizes SU2. SU2 is a 3-sphere. This will give us a 3-sphere. Now, we had this SO3 symmetry in the game to begin with. And in the nonlinear sigma model, the SO3 symmetry transformed the nonlinear sigma model field. So what happened to the SO3 symmetry? Well, it's actually realized as an SU2 symmetry that transforms this Z, which we can kind of think as the order parameter right now. And Z is 2-dimensional, so it's going to transform it in the fundamental representation of SU2. So there is a question about, why is it the symmetry fractionalization is with SO3 and not with Z2 times Z2? Well, this is why. The order parameter, or what will turn out to be the gauge charges are transforming in a projective representation of SO3. So they'll end up carrying, it's in the fundamental representation, so they'll end up carrying spin 1/2. So the fact that you have this symmetry fractionalization is why it's the SO3 symmetry that fractionalizes. So we're now considering these, degrees of freedom in G tilde on the sites. Well, that's a lot more than considering degrees of freedom with M. So we have too much. So we need to introduce some redundancy to compactify our G tilde back to M. And we can do that by, on the lattice edges, this is an edge labeled by ij because it's connecting the site I and the site j. We're going to introduce H tilde gauge fields. Remember, H tilde is the lift of H to the SU to a subgroup of SU2. And we'll have these gauge fields be in the fundamental representation of SU2 restricted to H tilde. So you can think that they're just built out of polymatrices. So, okay, why do we want to do this? Okay, firstly, why is it actually describing the order parameter manifold? Well, we have a gauge redundancy. Z is the same as H tilde Z, where H tilde is an element of big H tilde. And what this does is this compactifies the physical values of Z down to SU2 mod H tilde. But remember, H tilde, that was a lift of H to a subgroup of SU2. So this is the same as SO3 mod H, and that's the same as the order parameter manifold. For the people who know the Villain story, this is like saying, oh, I have G equals U1, and I can lift U1 to R, and the lift of the trivial subgroup of U1 gets lifted to Z. So U1 is the same as R mod Z. It's the same type of story as that. So you should, hopefully you're convinced that all the relevant information reflecting the universal properties of the symmetry breaking pattern are stored in this presentation. But where are the homotopy defects? Well, there's two places. Either they're stored in the lattice degrees of freedom, or the lattice site degrees of freedom, or the lattice edges degrees of freedom. Well, they're not stored in the lattice site degrees of freedom because SU2 is simply connected. So pi1 of SU2 is trivial. So they have to be stored in the gauge field degrees of freedom. And they are. Remember, these homotopy defects are classified by the conjugacy classes of H tilde. But in H tilde gauge theory, where H tilde is finite, which is in this case it is, the magnetic fluxes, or I guess I call them gauge fluxes here, are also classified by the conjugacy classes of H tilde. So these one-dimensional homotopy defects are exactly the H tilde gauge fluxes in this presentation. So good. So we have the right degrees of freedom that gives us good dynamical control over the one-dimensional homotopy defects. And now we can just write down the simplest Euclidean lattice model that we can from these degrees of freedom. So we've triangulated spacetime, so it's made out of a bunch of these three simplicities shown here. And the simplest action we can write down using A and Z from the last slide is the first term will be a combination of A and Z. You can think of this as like a Higgs term. And then the second term will just be the kinetic term of the H tilde gauge fields, where this is sum over the links and this is a sum over triangles like I, J, K. And this delta A is this shorthand for a product of the A's on the edges that go around the triangle. So we can get a quick idea of what the phase diagram is. This J term, the point in its life is to want the gauge charges or the Z's to condense. Right, but remember, the Z's transform under an SU2 transformation. So you should smell that there's some symmetry breaking that should happen as well. And you could show that with the SU2 transformation and the H tilde gauge fields, it produces a symmetry breaking pattern that's the same as SO3 gets broken down to H. So the Higgs phase of this model is the same as the ordered phase of this model, right? And furthermore, because the gauge charges are condensed, the gauge fluxes will confine. Remember, the gauge fluxes are how we're modeling the homotopy defects. So the homotopy defects will confine. And we know that means that any emergent asymmetry will not be spontaneously broken, right? What about when K is ginormous? Well, when K is ginormous, we can just drop the Higgs term. And then this Euclidean lattice action is the same as this normal H tilde lattice gauge theory. Right, so when K is ginormous, this is in the deconfined phase of H tilde gauge theory. And in the deep IR, you can actually describe those ground states by a quantum double of H tilde. And the there'll be a bunch of like a bunch of loops that condense. Some of those loops will be the symmetry charges, will be the homotopy defects or the gauge fluxes. So we'll have this symmetry breaking pattern. But there'll actually be additional symmetries that emerge, and those additional symmetries will also be spontaneously broken. So it's a little bit more complicated than only this. But I just want to emphasize that the emergent symmetry S is spontaneously broken in this phase. And then lastly, the SO3 symmetry is not spontaneously broken in this phase because it's a deconfined phase of gauge theory, and the electric matter, Z's, are going to be gapped. They're not going to be condensed. So I have -1 minute left. I want to go through one more example. It's only 3 slides, so I don't think it should take too long. And this is an example there were some very nice questions about earlier, and I hope this can elucidate some of those questions. So, fun with SO3 part 2. Now we're going to spontaneously break SO3 down to SO2. Of course, the order parameter manifold is a 2-sphere, and we'll live in d equals 4 space-time dimensions. So a 2-sphere, we're in d equals 4, so we only care up to pi3. Pi0 and pi1 are trivial. Pi2 and pi3 are both z. So what's the 3 group that describes this? Well, there's a bunch of datas, but because pi1 is trivial, a bunch of those datas are automatically trivial. All the pi1 actions, all those alpha, automatically trivial because pi1 is trivial. The only things that are non-trivial is the pi2 and the pi3, obviously, but also this Postnikov 4 invariant, which is a 4 cocycle. So this is a little bit abstract. How can we understand it? Well, one way to understand it is to introduce 2 and 3 cochains, x2 and x3, and they're going to be cochains on the classifying space of this 3 group. If you really want to be precise, what this is a simplicial set. And it's just a simplicial set that models the 3rd Postnikov stage of the 2-sphere. And you can get a feeling for what this beta does by looking at these cochains x2 and x3. I'm not going to argue it here. I don't have time. But x2 will be closed. So x2 is actually a 2 cocycle. But x3 is not closed. And you can show that d of x3 is equal to x2 cup x2. So this x2 cup x2 is at least how I would think of this Postnikov 4 invariant. So good, we have the 3 group. Now we know what the symmetry is because we just look at the magnetic symmetry of this 3 group gauge theory. The problem is this is a non-finite 3 group, so there's not going to be anything that's simple that has a label. However, we can at least smell if it's an invertible or non-invertible symmetry. So recall for normal groups, we were just looking at the Pontryagin eigendual. And that's how we could go from the symmetry charges being described by a group to giving me information about the symmetry defects. It turns out there's an equivalent thing for higher groups. There's a notion of a Pontryagin eigendual higher group. And whether or not that exists is something that's pretty complicated. I don't fully understand it. But something that my collaborators have told me is that if the Postnikov invariant is what's called a stable cohomology operation, then there should be a dual higher group, a Pontryagin dual higher group. As an example, Bochstein homomorphisms. Bochstein homomorphisms are stable cohomology operations. So if this 3 group, if the Postnikov invariant was described by a Bochstein, we would have a dual higher group. So the symmetry defects would be described by this higher group, and we would say, oh, good, we have this invertible symmetry. However, cup products, which is exactly this guy here, are not stable cohomology operations. So this seems to suggest there is not a dual 3 group, and instead it would be a non-invertible symmetry. And this is, and I think Shuhang in the chat mentioned, oh, doesn't this example have non-invertible symmetries? That's exactly right. This is what Chen and Tanizaki found. And here we also come to the same conclusion using our framework. So this is what the symmetry is. And now I just want to briefly give some intuition about what the non-trivial disordered phase looks like. And to do so, we'll construct an effective field theory for this non-trivial disordered phase. And we're going to kind of hack our way through it. We'll take motivation by considering what's called the CP1 presentation of the S2 sigma model. So in the CP1 representation, there's a U1 one-form gauge field, and there's also these complex spinors. And if you integrate out the complex spinors, you can actually get equations in terms of the gauge field A for pi2 and pi3. Pi2 will be the Chern number, and pi3, this will tell you what the Hopf number is, and it looks like a Chern-Simons term with a weird quantization. So I don't think you should take this expression too seriously. It's very particular for this CP1 model. But let's be inspired by it. And let's say, well, I really like dA. Let's include that in our building an effective field theory. So let's include this field strength dA. And I want to be inspired by this. I want to include this as a field strength, but it's not gauge invariant. So let's introduce a U12 form field B, such that this becomes gauge invariant, and we introduce this field strength H, right? So I just stuck out a 2 pi. So now this is my 3-form field strength. The fact this is gauge invariant means this is a normal 1-form gauge field, nothing special. The fact that B is gauge invariant, well, it'll shift by a normal exact form, but it also has to shift by something that has to do with A and F0 to ensure H is gauge invariant. And I think there's like a modified Green-Schwarz mechanism or something like this, that this type of gauge transformation comes up in 2-group gauge theory. It's the same as that gauge transformation, which is kind of interesting. So let's build an effective field theory from F and H. And we'll do it, this is very simple. Just have 2 kinetic terms, one from F, one from H. This is the normal Maxwell term. This is more complicated, right? This isn't Gaussian. It's not quadratic because there's this A wedge dA term. But we can get this in a more standard form. And we can do that by dualizing the 2 form to a compact boson. And if you do this, well, this term doesn't get effective. The Maxwell term comes along for the ride. This term does get effective. We have a kinetic term for our compact boson, but we also have this interaction term. And this interaction term is exactly the interaction term in axion electrodynamics. This phi is like the axion field, and this F is just the normal field strength of the U1 gauge field. So we can then propose the phase diagram. In the ordered phase, there's the normal SO3 to SO2 symmetry breaking pattern. And if you go to the non-trivial disordered phase, this effective field theory would describe deep into the IR. It's also well known this axion electrodynamics has a rich symmetry structure. I forgot to include the citations of this, but there's known to be higher group symmetries and non-invertible symmetries. And some of those non-invertible and higher form and higher group symmetries would reflect this 3 group, but there could be additional emergent higher form non-invertible, etc. symmetries as well. Okay, so that's the talk. Let me just summarize. We talked about how generalized symmetries emerge in generic ordered phases, and a general feature of the generalized symmetries is their symmetry charge was carried by what I call homotopy defects. And what we showed is that the symmetry defects are described by D-1 representations of some D-1 group. And this D-1 group is related to the D-1th Postnikov stage of the order parameter manifold. And then we talked as an application how we could spontaneously break this emergent symmetry and give rise to non-trivial disordered phases. And I think this emphasizes, in my opinion, the most powerful usage of these generalized symmetries in ordered phases is that it's a non-perturbative tool to identify exotic phases that neighbor typical common order phases. So thank you for everyone's attention. Thank you for the nice questions during the talk. And if there's any other questions, I'll be happy to take them now.
Hey, thanks a lot. Sounds like a really nice talk. There's actually one question in the chat by Hao Zhu. And the question is whether Toft anomalies are basically given in terms, captured in terms of the highest Postnikov invariant beta.
Oh, that's a good question. I don't think that's the case. So let's go back to all the datas of the Postnikov invariants. So suppose this was a simple 2 group, and there'd be an H3 Postnikov invariant. Just because there's an H3 doesn't mean that's a Toft anomaly, but it is related to Toft anomalies in the sense that if you gauge the one of the symmetries, that H3 class will describe what the Toft anomaly is. So I don't think any of these Postnikov invariants are related to the Toft anomalies. But thank you for the question. It's a very interesting question.
So I have 2 questions. So you discussed about the symmetries in the infrared. They do not capture all the emergent symmetries, right? So the example
I didn't hear what you said. What symmetries did you say in the beginning?
The emergent symmetries.
Yeah.
Yeah. Can you hear me now?
Yeah, I can hear you.
Yeah, so they do not capture all the emergent symmetries, right? So the example I have in mind is in two space-time dimensions. If you consider Z2 spontaneous symmetry breaking, then the total number of emergent symmetries would be described by a multi-fusion category, which is given by 2 by 2
Good.
matrices based on vector spaces. So that does
Yeah,
include,
thank you.
but not all of
Yeah,
it.
thank you. Yeah, you're totally right. This is exactly related to when I said that we're going to consider general connected M, right? You're totally right. If you have disconnected M, you'll have a D-1 form symmetry. And because of that, yeah, you won't have fusion D-1 categories. You'll have multi-fusion D-1 categories. And yeah, these D-1 form symmetries are not included in this. You're right. This is not the most general thing. This is only for a connected M. It's the zeroth order thing to sit.
I think in that case,
Yeah,
we talk about representations of a higher homotopy groupoid.
Let's see. And that would
yeah,
be the
I think that I think that's right. The only thing I'm uncertain of is how I don't know if this D-1 form symmetry, how that would interact with the other homotopy groups. But yeah, this higher groupoid would probably encode that, right? I just don't know it.
Thanks. So I have one more question. You're considering spontaneous breaking from G to H. Do you also allow
That's right.
SPT phases for H?
That's an excellent question. I didn't think about that at all, but I think it would be interesting. I didn't consider that. But yeah, maybe the SPT phases and these emergent symmetries would have some interesting interplay. But no, I always assume that the residual symmetry forms a trivial SPT phase. That's right.
I see. So the reason I'm asking is because I think, I mean, at some point you gave us a philosophy that generalized Landau paradigm should be about emergent symmetry. I think that's only one piece
That's
of
right.
because it won't include these SPT phases. So in general, you have to provide a map from ultraviolet symmetries into infrared symmetries, including the emergent infrared symmetries. It's also this information of a map, and that map can have a kernel. So what you're pointing out is that there can be non-trivial co-kernel for this map, but there can also be non-trivial kernel, and you have to include both of these.
I totally agree. You're totally right. I really should have said that it's a classification scheme about the microscopic symmetries and the emergent symmetries, or more precisely, it should be the IR symmetries, because you have UV symmetries, you have this map from SUV to SIR. It's really a scheme about what SIR is. Would you agree?
Yeah.
Okay,
yes.
Great. Okay, thank you for your question. Nati, you have a question?
Yeah, I'm actually a little bit puzzled about your generalized Landau. Because you could get a lot of emergent symmetries which play no role whatsoever. They do not correspond to anything in the IR. So it's hard for me to see how you can base a classification on them. For example, let's take your nonlinear sigma model. If we are strictly in the infrared, it has only massless pions, and we don't see the curvature of the field because of the target manifold, because it's an irrelevant operator. So what we see is massless free fields. So strictly speaking, the IR CFT, or the IR field theory, is a theory of non-compact free fields. And there are lots of them, and they have lots of symmetries, but I doubt you will get a lot of mileage out of it. The mileage you got in the non-linear sigma model is from the topology of the target space, which is not strictly infrared thing. So it's hard for me to see how relying too much on emergent generalized symmetries would give you a classification.
No, that's an excellent point. What I really mean by this second bullet point, I think this is too strong of a way to phrase it, and the strength of it isn't. I didn't think about it that precisely in this wording. What I really mean is to say that in my experience, when I've talked to people about generalized Landau, their response is, "Oh, there's no exact higher form symmetries or these generalized symmetries don't appear in the Hamiltonians I have. Why should I care? And all I'm saying is, well, we should include the symmetries that emerge as well, because those could classify phases. Maybe it's not, yeah, I think it's given the comments, that's not enough. You need to include additional symmetries if you're going to have a generalized Landau paradigm, because they can have SPTs. But that's all I'm saying.
But even before SPTs, I think I'm really underscoring what Lakshya just said, that you really need more information from the IR, from the UV, about the kernel and the co-kernel. And the co-kernel, I think, plays a secondary role. It's the kernel that would be interesting.
Okay.
Because it's easy to write examples which have emergent symmetries and which are of no significance at all.
So in addition, so the kernel will tell me what symmetries trivialize. So that could tell me things about SPTs. But it isn't clear to me what else they could tell me in addition to SPTs. Is there anything you're particularly thinking about?
Well, there are lots of examples of emergent symmetries that are proximate symmetries, and therefore they are not that significant. The XY
yeah, I don't
model,
think I'm saying.
If you put too much weight into emergent symmetries, you would say that the C=1 boson does not have a BKT transition. Because the BKT, if you start from the XY model without the winding symmetry, then there is a BKT transition, but you have an emergent symmetry which has that of the winding symmetry.
Good. Yeah. So, yeah, I guess what really I'm saying is that if we're going to have a classification scheme based off symmetries, we should take emergent symmetries seriously. It doesn't mean they're always going to be some, gift from the heavens that will classify things, but they can be. And I think the gauge deconfined phases of gauge theories are great examples of their power, which you know. So.
Okay, I also have another question regarding your Villain presentation of this O3 sigma model, where you gauged. So let me see if I understand. You gauged some non-abelian group. What is it, quaternion or D4 or whatever, a subgroup of SU2. That's your gauge group.
Yeah, this H tilde. So like, if H was Z2 times Z2, H tilde would be like the quaternion group. That's exactly right.
Right. Okay. And then you wrote some term for the kinetic term, which I think the coefficient was K, if I'm not mistaken. That's right.
That's exactly right.
And that's an action, right? So this is an action in some classical statistical mechanics.
That's right.
Right. Does it have the magnetic symmetry or not, as it stands?
That's a good question. I think strictly speaking, that would only be an exact symmetry when K is infinity. Alternatively, I could write this with some Lagrange multiplier that would force trace of this to be 1. And only when trace of this is equal to 1 exactly on the nose is the Wilson loops topological.
Right.
But I want to think of like the limit of K going to infinity is essentially enforcing that this is equal. Maybe I would put like 1 minus this or something, but
okay. So
I think only when K goes to infinity.
Okay, so the discussion below is only when K is infinite, or not?
I think this phase diagram is for finite K. It's just the statement that, well, when K is infinite, maybe we have this exact symmetry, whatever this one non-invertible one form symmetry is. But because emergent higher form symmetries are exact at the energy scales they emerge, you could still have this whole entire phase that is characterized by the symmetry breaking. It's just like in toric code, you have these exact one form symmetries, they're spontaneously broken, but you could perturb the toric code and explicitly break the one form symmetries. But you still have the topological phase persisting away from the toric code point. That's how I'm viewing this phase diagram. So this would be like the toric code point, which is to say it's described by the quantum double of H tilde.
It's stronger than the toric code. It's the toric code when some of the terms were set to 0, to infinity. So the Gauss law is strongly enforced. It's not strictly the toric
yeah.
code.
Yeah, you're right. It's like the topological toric code. Yeah, when all
But
when all
also
the
known
coefficients of
as the
infinity.
Z2 gauge theory.
That's right.
The whole beauty of the toric code is that you added these terms, so it's not just a Z2 gauge theory. There's more stuff in it. But the limit you take is to throw away all this stuff.
Yeah, I think what do I want to say? Yeah, there's this condensed matter perspective where we always want our Hilbert spaces to be tensor products. And I know you have a lot to say about that. But that's why I was saying toric code first. But you're totally right. Yeah. Cool. Are there any other questions?
Thank you. This was very nice.
Yeah, thank you so much, Nadi.
Okay, I don't see any other questions. Let's maybe stop the recording and then thank Sal again.